Hey everybody, this is going to be a brief tutorial on drawing and naming various types of simple carbohydrates. And I have a couple examples that we'll step through in this video. I'm going to break them down in the table of contents here. So if you don't want to watch the whole video and you're just interested in skipping to the end to look at disaccharides, that's totally fine. I will meet you there. But just be aware that you can do that if you want to pick out a specific portion of this to review. First, though, before we get to some of the more complicated structures, I want to review a typical type of problem that we would potentially see here, where we're just being asked to draw a particular sugar structure, and we need to know some things in order to do that properly. So, going through this real quickly, I need to identify a few things that I'm being asked for, all right? First of all, this problem gives me the common name for this particular monosaccharide here. And it also gives me some information about it. First of all, really important is just the enantiomer that I'm dealing with here. So I know it's a D enantiomer of this monosaccharide maltose. We also know, because we don't have a structure handy, we're gonna have to make that ourselves. This is an aldohexose. And we're also given some information so that we don't have to look it up in a reference table that tells us the orientation of a couple of the carbons on, or the hydroxyl groups on those carbons in the chain, right? So all this should be enough information for us to make the structure that we're being asked for, which is a 6-membered ring version of this, where the anomeric hydroxyl is in the cis configuration, okay? So we'll step through each of these things in turn, but those are the important parts of this that we need to identify. So first things first, I'm going to check off my aldohexose box here. I need to make a structure that's consistent with that. So hexose means 6 carbons, and the aldo part of that means that carbon number 1 in this chain, I'm going to draw a chain of 6 carbons on my slide here for the linear structure to start with. All right. The top carbon, carbon number 1 here, is going to be the carbon that is the anomeric carbon that has the carbonyl carbon in the linear structure. So this is an aldose. So we have an aldehyde group up at the top here. And we have the end of our chain, as always, is not going to be a stereocenter. So we can fill that in as well. We're told that this is a D enantiomer of altrose. So that gives us some extra information as well. That specifically tells us about carbon number 5 here. Carbon number 5 has to be in the D configuration because that second to last carbon in the chain is the one that defines whether our sugar structure overall is D or L. All right, so that's another clue from the name. And then we're just getting a bunch of information to fill in the rest of the structure. So carbon number 2, we are told, is in the L configuration. So I'm going to draw the hydroxyl on the left in my Fisher projection. And then the other 2 are D. So I'll flip it for carbons 3 and 4. All right. So this is how we get our linear structure based solely on the structure or information that we were given at the beginning of the problem, right? So now the challenge is to fold this into a ring. And we're given some very specific information about how we're supposed to do this. It needs to be a 6-membered ring at the end of the day with the anomeric hydroxyl in the cis configuration. So let's step through this real quickly. I actually want to show us one just important thing to mention about the possibilities here, right? First of all, we've talked mostly, and we often do, about structures where this second to last hydroxyl, which has some extra electrons on it, right? This is going to precipitate a nucleophilic attack on that carbonyl carbon that's up at the top. And we're going to end up with a 6-membered ring if we do that. So that's what we want to do. But I want to just highlight the fact that there are other possibilities here, right? If the hydroxyl in the number 2 position comes up and attacks this ring, we would end up with a 3-membered ring here, right? The reason we don't see that very often, that would be 2 carbons and 1 oxygen there. The reason we don't see that very often is that a 3-membered ring is really strained. And it's not very common in organic chemistry. Those are very unstable structures. Carbon number 3 here, similar situation, right? If this attacks the hydroxyl or the carbonyl carbon up there, we're going to end up with a 4-membered ring. And that is also not ideal sterically. the ring strain there will be too great, and we probably won't see that structure much in solution. We could, if we wanted to, make a 5-membered ring by attacking the carbonyl carbon with that carbon number 4. That would give us a 5-membered ring. And that's totally fine. We could do that with this structure. And then we'd have a couple of carbons outside of the ring, and there would be some stereochemistry there. So that's one potential option, but that's not what we were being asked for here. We were being asked for this final scenario where the carbonyl carbon is attacked by carbon number 5. This creates a 6-membered ring, and honestly, this is probably going to be the dominant structure in solution anyway, because this creates sort of the ideal size of a ring that will create an environment where all those tetrahedral carbon atoms are going to be happy. All right, we could, in theory, do a 7-membered ring down here, and if this one attacks the carbonyl carbon, we would have that as a possibility. If I can draw a 7-membered ring here, right? But that is something that is probably not going to happen either, and it has to do with steric hindrance in the ring. So we don't usually see 7-membered rings very often either, right? So just a quick overview of all the possibilities here, and I want us to be aware of the fact that there are all these possibilities technically, but 5- and 6-membered rings are definitely the ones that we're going to see most often, right? So I'll get rid of all of this, and we can get back to actually drawing our structure here. Because we know that we want a 6-membered ring. It's always good to check that that's what we're going to end up with. And as we've just verified here, the 6-membered ring that we actually want is the one that forms when this carbon number 5 hydroxyl attacks. So we've got this set of atoms that will now be part of a ring together. And we know that once this happens, there will be some electrons that move up to this oxygen that used to be part of the carbonyl group, and there will be a proton transfer where we'll eventually lose the proton on our hydroxyl and carbon number 5. That will end up here, and that's eventually what our structure is going to look like. So drawing that out, we have some shortcuts that we can take. I always recommend, right? This is a classic structure that we're going to assemble here. I always recommend that we kind of set it up this way, where the oxygen that ends up in the ring is on the top right here. This just gives us a nice kind of standard way of looking at a sugar. And then if we number around the ring, we have carbon number 1 right in the ring there, and we're going to number clockwise kind of by our convention here. So that's where all those carbons ended up. And I'm going to put carbon number 6 coming out of the ring and up, like so, right? And its hydroxyl group will be sitting out of the ring just like that. So we'll have a couple of hydrogens to draw in here. So then the question is, what do we do with the rest of this? And the main rule that is helpful when you set up something like this, where you've numbered the carbons in the clockwise direction, and your carbon number 6, your final carbon that's not part of the ring, is oriented up out of the ring, you can use a trick where this is sort of one that will work universally for D enantiomers here, where if you set your structure up like this, our D hydroxyls will be oriented down in the ring, right? And this will work for a D enantiomer of any sugar, and we can just follow that rule as long as we've sort of set up the template structure in the way that I'm showing on the slide here. So that's one thing we can use going forward. All right, I'm going to start with carbon number 4. I can see that that's in the D orientation. So if I draw my Hayworth projection here, where we're showing up and down in the ring like this, I have that in the D orientation. So I should draw my hydroxyl downward. Hydrogen will be facing up. Then I move to carbon number 3. This is also in the D orientation, so that will be pointed down as well for this structure. Carbon number 2 is the weird one. That's the one where we have it oriented up in the ring because it's an L orientation. And then we get to the anomeric carbon. And this is the one where we actually have a choice, because the hydroxyl that we're going to draw here is the hydroxyl that we highlighted over here earlier as being the one that's created when the ring forms. It didn't used to be a hydroxyl, it used to be a carbonyl group. And depending on which side of the ring, or which side of the carbon this oxygen down here attacks, we could end up with that hydroxyl in either orientation. And so that's why it needed to be specified in the question if I wanted you to give me something specific. So in this case, we want it in the cis configuration. What we always mean by that is that we're sort of doing it relative to this carbon number 6 group that is up and out of the ring here. So if we want that in the cis configuration, what I mean by that is that the hydroxyl group should be on the same side of the ring as that carbon number 6. All right. In a projection like this, where you're drawing a D enantiomer here and you're labeling the carbons clockwise like so, the hydroxyl in the cis configuration will always be oriented up. The other name for the cis configuration here is the beta orientation, right? As opposed to alpha, which is where it's on the opposite side. So now we just have to name this sugar, and we have the common name already given to us. So we're just going to add a few things to it. Start out with the name D-altrose. And what we're going to append to the beginning is the orientation of that anomeric hydroxyl. Okay, so we just add a beta. We don't need to do this when we draw or we're trying to name a linear structure. Alpha and beta only come into play when we form the ring, because they refer to a hydroxyl group that wasn't there before, before we cyclized the sugar. So that's one thing we have to add. The second thing we have to add is a part of this name that specifies how many members are going to be in the ring, how many atoms. And since this is a 6-membered ring, the name for this is pyranose. Okay, so that's the base sort of suffix that we're going to use to talk about this. I'm going to chop off a little bit of my name here. This can always get tricky, and if you're in my class, I probably won't mark off for spelling here. But that's what I would end up with for my final name. I would just append pyranose to the end there to specify that I'm dealing with a 6-membered ring. All right, and now we have all the information we need in that name to reconstruct that structure. All right, so there's one example for us. Taking a look at another one, we're going to go ahead and just dive right in to this one. It is a ketohexose this time that we're working with. So that's one piece of information we need. I've got the name, including, at least for starters here, including the orientation, the enantiomer, common name, which will eventually be useful. And the information I'm being given in this first sentence has to do with the D enantiomer. So I'm going to draw that out first, and then I'll see what else I'm being asked for in this question. All right, so a ketohexose has 6 carbons. And so I'm going to write that down on the slide and sort of diagram out my structure. I can fill in a couple of details right away. The first is just like an aldose, we can put a non-stereo center at the very end of our chain. I'm going to label these carbons again so we can keep real careful track of them as we draw the rest of our structure. Now, a ketose is different from an aldose because it actually is a ketone structure. And there are a bunch of different ketoses that we could draw, but typically when you're just being asked about a regular old ketose sugar, what they're referring to is a ketose where the carbonyl carbon is on carbon number 2. All right. There are other versions of ketoses that have that carbonyl carbon somewhere else in the chain, but the most common ones, the most relevant ones are that we're going to study typically are the ones where we have a 2 ketose, or a ketose where the carbonyl carbon is carbon number 2. Right. So that's our only real choice there. We also have some other information. Again, this is the D enantiomer that I'm drawing right now, and I'm going to fill that in. Our second to last carbon is going to have that orientation just because it's a D enantiomer. And then we've got D orientations for carbons numbers 3 and 4 as well. So here we go. That's our structure. So this is D-cyclose. Okay. Now let's skip down and see what it wants us to actually draw here, this problem. It says draw and name the structure that results when L-cyclose forms a 5-membered ring with the anomeric hydroxyl in the trans configuration. So here's the part where we're sort of thrown for a loop. We're actually supposed to be making the structure of L-cyclose. All right, a couple of different ways we can do this. We can, if we were going to draw the linear structure of L-cyclose, okay, I will very quickly do that on the slide here. It's going to look the same, except we're going to take every stereocenter and we're going to flip it. So I'll finish my template structure here with 6 carbons. Right, I've drawn all the non-stereocenters to start with, but if we wanted L-cyclose, the Fisher projection would look like this, right? With everything oriented on the left, we have a stereocenter. So this is L-cyclose, right? We have a few different options for how to deal with this. Technically, we've got L-cyclose now. We could use that as a template structure. Ultimately, you're going to have to end up with a structure that is a mirror image of the D enantiomer. So a couple different strategies. The first strategy is just to look at our D structure over here first and just draw that structure and then flip it when we're trying to draw the ring cyclic structure. That's probably one of the easier things we can do. So I'm going to go ahead and make my 5-membered ring, and I'm going to make it for D-cyclose first, and then I'm just going to flip everything at the end, and that'll be my final answer. Okay, I'll mirror it across the page. So I'm going to label my carbons real quickly here. Remember that in this structure, we're forming a 5-membered ring. We have to make sure we know how to do that. Turns out that if you take this carbon number 5 in our chain and you attack our carbonyl carbon here, you're going to end up with 1, 2, 3, 4, 5 members of our ring. And that's going to give us a 5-membered ring that we are looking for. So that's the structure that's going to form. And it's really important to keep track of the numbering here. The anomeric carbon, in this case, the one that actually gets attacked by the oxygen, is carbon number 2. So if we're labeling our ring, try to do this clearly on the slide here, we have carbons 2, 3, 4, and 5 in the ring, and carbon number 1 is going to be out of the ring here, right? That's not part of the ring structure, same as carbon number 6. Okay, we know what to do with carbon number 6. That's pretty common to just put that oriented up with our structure labeled clockwise. So that'll be in this position. Carbon number 6 is up here. All right, and then we can follow our normal conventions. D configurations on our hydroxyls are going to result in a down configuration, just like before. So I'm going to fill this in and add 2 D conformations to carbons 4 and 3 here as I make my way around. Now, carbon number 2 is the anomeric carbon. So this is where the trans configuration is the part that we need to pay attention to. That trans configuration is referring to the hydroxyl. So when we put this in the trans orientation like this, which means, in other words, it's opposite side of the ring from our carbon number 6 on this side, this is our alpha configuration. But we're not quite done with the structure yet, because we still have to worry about this carbon number 1 up at the top of our structure, right? And so that one actually ends up outside the ring as well. And this is what we're going to look like, right? Carbon number 1 is not a stereocenter in this structure, so I don't have to specify its conformation exactly, but it is going to be outside of the ring, right? So this is, if I was going to be really specific, I'm going to follow my same naming conventions. So I take my D-cyclose root, and I'm going to add an alpha to the beginning of it to specify the orientation of that anomeric hydroxyl. And then because we're dealing with a 5-membered ring, this is where we use the suffix furanose, which is the base structure for a 5-membered heterocyclic ring with an oxygen in it. All right, so I'm going to just chop off a little bit of this name. Instead of cyclose, I now have cyclopyranose. Sounds pretty awesome. So that's the structure that we're going to make if we make the D enantiomer. But we weren't asked for the D enantiomer, so we're not quite done. We were asked for the L enantiomer. So I am just going to take this structure and mirror it across the page. Okay, and I'll try to draw this very cleanly over here so we can really see everything properly. Okay, we have carbons. Oh yeah, so now we've mirrored everything. So our carbons are labeled counterclockwise now, right? Carbon number 6 is still up and out of the ring like this, but now it's just a mirror image of what we were working on before, okay? And we're still going to draw everything in the appropriate orientation, but our structure is now sort of mirrored or backwards. And that's what we're left with. This is alpha L cyclopyranose, right? That is where we're gonna leave this structure, okay? Hopefully we can kind of recognize here that we could have taken a little bit of a shortcut if we were given the information for the L enantiomer first. So say you only had this, right? And maybe this was the initial information you were given, and the first structure that you drew was the L enantiomer. Okay, say we didn't draw the D enantiomer first. You could cut a lot of corners by simply setting up your structure so that you're labeling it in the counterclockwise direction. So we know we need a 5-membered ring, right? Rather than labeling it clockwise, we're going to label it counterclockwise this time, which is what we ended up doing at the end there. And so we end up with a template structure that looks kind of like this. And then we just have to flip our convention for drawing our enantiomer versions of these hydroxyl groups. So now when we do this structure, we're going to set this up so that when we see an L configuration, it's pointed down, right? We're in the mirror universe now, and we're just gonna do everything backwards from the way we were doing it before. And that will also produce the correct structure in the end here. Okay, so there's a number of different ways to think about this, but a couple different options for you. All right. Finally, I want to get to talking a little bit about just the way that we put together disaccharides. So now we're going to polymerize multiple monosaccharides together. And I'm just going to use the ones that I was working on the previous slide. So I have copied these structures from our previous slides. That's all I've done here. And we can kind of pick up where we left off. Remember, again, this was beta D ultra pyranose being a 6-membered ring with the beta conformation on the anomeric hydroxyl. And the one on the right here is alpha L cyclopyranose. All right, so these are structures we did in the earlier parts. And now we just have to put them together into a couple of different disaccharides. So we are asked for 2 different versions of this. We are asked for a reducing disaccharide and a non-reducing disaccharide. So I'm going to go ahead and draw these for us and proceed to name them as well. So we're going to take this. I'm going to maybe just simplify my diagrams a little bit by leaving out the bare, the hydrogens that are present here, just so that I can draw a simpler structure. But hopefully that won't be too confusing. Remember, with reducing sugars, we have a bunch of different options, right? We can use an anomeric hydroxyl if we want to. So maybe I will in this case. Maybe I'll use this carbon number 1 on our altropyranose. I will take that as one example. And then I have every possibility here for a reducing sugar, except since I'm already using one of my anomeric hydroxyls, I cannot use the other one because that would make it into a non-reducing sugar, right? Where both anomeric carbons are tied up and can't open up again. So I'll pick something else. Maybe just to make things simple, I'll pick carbon number 3 here as the joining point. So we're going to convert those hydroxyl groups into a glycosidic bond that links them together. That'll be part of a condensation reaction. And that's what's going to generate our final structure here. So real quickly, I'll draw that out on the slide. We have our constituent sugars. And again, I'm going to leave out a little bit of detail in the interest of kind of making this a clearer picture. But I'm going to draw in the hydroxyls here so we know where those are. And hopefully we agree that this is a fair representation of what we're starting with. Okay. And then our other sugar is our L-cyclofuranose, which is a 5-membered ring. And this one has 2 hydroxyls coming off of that side of the ring. And then we've got my hydroxyl pointed down. That's the one I'm going to use for my bond. Another one pointed down. And then another hydroxyl coming up and out of the ring on the other side. So these are our 2 sugars that we're starting with. Now, to form the bond here, what I'm going to do is take my 2 groups I'm interested in. I'm just going to erase their hydroxyl groups, put an oxygen between them, and all I have to do is find some way to link those groups together, like so. Okay. And what I have done is created a glycosidic linkage between these 2 sugars. And the way I would write out this structure, I'll probably just go left to right here, but you could put either sugar first in this name. That would be fine. But the first sugar in my group is beta D ultrofuranose. And because it's the first one that I'm naming, I'm going to add this little substituent name, a little suffix onto the end of it, because technically the correct way to name these is to just sort of add that as a sort of an IUPAC substituent suffix, if it's not the last sugar in the chain. Okay, then the next part is the most important part, the only piece of new information that we have or need, which is that when we did this linkage, we bonded carbon number 1 in this chain here. I'll use a different color for that. Carbon number 1 with carbon number 3 on the other sugar. So the first number here, which refers to, this sugar that we've already laid out, that one needs to come first, and that's carbon number 1. And then we have a little arrow in our notation to a 3. And close our parentheses. And now the next part of the name is going to be our second sugar. So I'm going to say it's alpha L-cyclofuranose. So that's our full name. We have literally just taken the individual names for the ringed sugars and we've slapped them together, and we've added a little bit of new information that shows how they're attached to each other. We know we have a reducing sugar because one of those anomeric hydroxyl groups is still free, which means that this sugar can potentially open back up and at least on the furanose portion of the sugar, and can potentially participate in different reactions. That's why we refer to it as a reducing sugar. Whereas the one over on the pyranose is sort of stuck like that, much less reactive in that part, in that configuration. So I'm going to go ahead and erase this, and we're going to do our second example, or I'll erase some of it anyway, because I can keep our structures. I'll get rid of the name, and I'll get rid of our glycosidic linkage here, and just kind of redraw some things. And now that we've reset, this will be part B, where we want to make a non-reducing sugar. I've already alluded to how we do this, not much of a change, right? This is, again, the structure that we're starting with. And this time, we need to bond our anomeric carbons together so that we tie both of them in. And this would be carbon number 2 on our ketose and carbon number 1 on our aldose, just like before. So again, what we're going to do is erase from my structure both of those hydroxyl groups that are going to participate and put a little oxygen between them, and then just sort of find some way to make the bonds work so that these structures are bonded together. So not too much of a change, but we have changed the nature of the sugar pretty significantly, because now neither one of these ring structures can open back up, which is what is going to help us define this as a non-reducing sugar. So once again, we just start out with our name, where we have, I'm just going to do this left to right, just like before. We have beta D ultra pyranosyl, and then the linkage. So this is the part that changes, right? We have carbons 1 and 2 interacting with each other. So that's what I need to write, and those need to correspond to the left and right sides of my name here. And so that's what I have written down now. Then we're going to do our second structure, and this will be psycho. And I could go ahead and try to name this with my normal name. I could just end it with furanose, except that to be perfectly accurate here, we do have a little bit of a different functional group taking place on this second sugar that is part of my name. Now that I have that anomeric carbon tied up, this is no longer a hemiketal, which is what it was strictly speaking when we were working. Now I have a full ketal there. And so what to be perfectly accurate here, I'm going to end my name with the suffix furanoside to indicate that I have a full ketal there instead of a hemiketal now. We would have done something similar over on this other carbon here, which of course is also tied up in the glycosidic linkage. And so this is actually an acetal group instead of an hemiacetal, which is what it was before when the anomeric carbon was free. But because it's the first name that we put in our naming structure here, it just gets this little YL substituent group kind of suffix. So we don't have to worry about naming that one differently, right? These are really minor details. The major piece of information, again, is just this linkage information that's in the middle and is bounded by parentheses there. That really tells you the new stuff that you need to bear in mind when you are putting these two sugars together, right? So hopefully that all makes sense. I hope this was helpful. We've looked at monosaccharides and disaccharides in this video, and I think that's where we're going to leave it for now. So thanks for watching.